Once the window is valid, you update your answer. This usually means something like tracking the characters in the window to see if they meet some condition. If the window is invalid, you start removing elements from the left and shrinking the window until it becomes valid again. Now, let's see these two templates in action.
Let's put the fixed size sliding window pattern into action with this problem. Maximum subarray of length k. We're given an array of non-negative numbers and a number k, and we need to find the largest possible sum of any subarray of length k. Since the subarrays must be exactly length k and consecutive, this is a perfect case for a fixed size sliding window. So here's how we solve it. First, we build the initial window by summing up the first k elements of the array. That gives us a starting point to compare against. We store that in a variable called windowSum. Then we copy that into a largest variable, since this is our first and currently best subarray sum. Next, we slide the window forward through the rest of the array. We do this by looping from index k all the way to the end of the list. Each step forward means one number falls out of the window on the left and one new number enters on the right. So first we figure out the index of the element that's now outside the window. That's right minus k, which we call left. Then, we subtract nums at index left from our window sum, since that value is no longer in the window. Next, we add in the new number at nums at index right, which just entered the window. Now that our window is updated, we check if this new sum is larger than what we've seen before, and update largest if so. We repeat that process until we've scanned the entire array. Finally, we return largest, which will hold the maximum sum we've found across all k-length windows. This is a classic example of how sliding window avoids extra work. We're not resumming each subarray from scratch. Instead, we're just adjusting the total by removing one number and adding another. Time complexity stays linear big O, which is exactly what we want in an interview. And that's it, smooth and efficient. Alright, let's try another real coding problem. And this is a perfect case for we're given an array of non-negative numbers and a number k, and we need to find the largest possible sum of any subarray of length k. Since the subarrays must be exactly length k and consecutive, this is a perfect case for a fixed size sliding window. So here's how we solve it. First, we build the initial window by So here's how we solve it. First, we build the initial window by summing up the first k elements of the array. That gives us a starting point to compare against. We store that in a variable called windowSum. Then we copy that into a largest variable, since this is our first and currently best subarray sum. Next, we slide the window forward through the rest of the array. We do this by looping from index k all the way to the end of the list. Each step forward means one number falls out of the window on the left and one new number enters on the right. So first we figure out the index of the element that's now outside the window. That's right minus k, which we call left. Then we subtract nums at index left from our window sum, since that value is no longer in the window. Next, we add in the new number at nums at index right, which just entered the window. Now that our window is updated, we check if this new sum is larger than what we've seen before, and update largest if so. We repeat that process until we've scanned the entire array. Finally, we return largest, which will hold the maximum sum we've found across all k-length windows. This is a classic example of how sliding window avoids extra work. We're not resumming each subarray from scratch. Instead, we're just adjusting the total by removing one number and adding another. complexity stays linear big O, which is exactly what we want in maximum sum we found across. Right. Let's try another real coding problem. And this one's a textbook example of when to use a dynamic sliding window. Find the length of the longest substring without repeating characters. We're given a string, and we need to find the length of the longest substring that doesn't have any repeated characters. This kind of problem is perfect for the sliding window pattern because we're working with contiguous characters and we need to grow and shrink the range based on some rule, in this case, uniqueness. Let's look at a quick example to build some intuition before diving into the code. We'll use the input string ABCDBEA and walk through how the sliding window works. We'll start with both pointers, red on the right and blue on the left, at the first character. That gives us the substring A, which is valid, and its length is 1. Now we move the right pointer to B. Our window is now AB. No repeats, so we update our longest to 2. Add C to the 3. Add D. We've got ABCD, all unique, longest becomes 4. Now we hit a repeat. We add B, and that gives us ABCDB. But B is already inside the window, so this window is invalid. To fix that, we slide the left pointer, the blue one, forward, one step at a time, until B is no longer duplicated. We remove A, then remove the first B. Now we're left with CDB, which is valid again. Next, we add E. the window becomes BCDE. No repeats, but the length is still 4, so longest doesn't change. Add A, now it's BCDEA. All unique again, and now we have a new longest of 5. At this point, we've scanned through the whole string, and we're done. The final answer is 5. Now let's walk through how the code captures that exact logic. We start by setting up 2 variables, longest, which will track the maximum substring length we've seen so far, and L, which marks the start of our sliding window. We also set up a dictionary called counter, which keeps track of how many times each character appears in the current window. So far, 2, all unique again, and now captures that exact logic. We start by setting up 2 variables, longest, which will track the maximum substring length we've seen so far, and L, which marks the start of our sliding window. We also set up a dictionary called counter, which keeps track of how many times each character appears in the current window. We use default dict so that every character automatically starts with a count of 0. Then we loop through the string using a right pointer, R. For each character at index R, we add it to our window by incrementing its count in counter. Now here's the important part. If the character we just added appears more than once, that means we have a duplicate, and we need to fix the window. So we use a while loop to shrink the window from the left. We subtract 1 from the character at the left pointer and move L forward by 1. We repeat this until the character count goes back to 1, meaning the window is valid again. Once the window is valid, we calculate its size using R minus L plus 1. And if that's larger than our current longest, we update it. This process continues as we scan through the whole string, always expanding the window from the right and shrinking from the left as needed to maintain uniqueness. At the end, we return the value of longest, which gives us the length of the longest substring without repeating characters. This is a great example of a dynamic sliding window in action. You're not just moving across the string, you're constantly adjusting the window to match the rule you're enforcing. It's efficient. The time complexity is linear big O since every character is visited at most twice. And the pattern is super reusable. Once you get comfortable tracking conditions like no repeats inside the window, you'll start to see this technique everywhere.
Binary search is
The window, you'll start to see this technique everywhere. Like no, and the pattern is super reusable. process of at index r, we add it to our window by incrementing its count in counter. Now here's the important part. If the character we just added appears more than once, that means we have a duplicate, and we need to fix the window. So we use a while loop to shrink the window from the left. We subtract 1 from the character at the left pointer and move L forward by 1. We repeat this until the character count goes back to 1, meaning the window is valid again. Once the window is valid, we calculate its size using r minus L plus 1. And if that's larger than our current longest, we update it. This process continues as we scan through the whole string, always expanding the window from the right and shrinking from the left as needed to maintain uniqueness. At the end, we return the value of longest, which gives us the length of the longest substring without repeating characters. This is a great example of a dynamic sliding window in action. You're not just moving across the string, you're constantly adjusting the window to match the rule you're enforcing. It's efficient. The time complexity is linear big O since every character is visited at most twice. And the pattern is super reusable. Once you get comfortable tracking conditions like no repeats inside the window, you'll start to see this technique everywhere.
Binary search is one of the most efficient algorithms in all of computer science. At its core, it's a way to take a big problem and cut it in half over and over again until you land on the answer. And that's the key idea. Cut the problem in half at every step. Instead of scanning the array from start to finish, which would take O of n time, binary search lets you find the answer in O log n time. But here's the thing, binary search is so much more powerful than just searching for a number, and most people don't even realize it. So let's start with the basics, and then we'll generalize it to see how truly powerful it is. But first, the intuition. Imagine you're playing a number guessing game. I pick a number between 1 and 80, and you have to guess it in the least amount of moves. Each time you guess, I tell you if it's too high or too low. What should your first guess be? Well, you would probably guess 40 because it's right in the middle and you can automatically eliminate half the answers. Now, based on this answer, you would then make another guess and cut the range in half again and again, and so on until you find your answer. That's essentially what binary search is. Each guess lets you eliminate half the remaining options. And that's what gives you logarithmic time. You can even go from 1 million down to 1 in just about 20 steps. Far more efficient than scanning all 1 million values, which would take at worst 1 million steps. Now, let's take a look at starting with the binary search template that you might recognize.
Let's start by taking a look at the vanilla binary search template, which is what most people may recognize. Now, let's break down how this vanilla binary search algorithm works line by line. This is our function definition. We're given a sorted list of integers AR and a target number that we want to find the index of. We set 2 pointers. Left starts at the beginning of the array and right starts at the end. These define the current search range we're looking at. This loop runs as long as there's something to search, meaning our left pointer hasn't passed the right one. Once they cross, we know we've exhausted the search space. We calculate the middle index of the current range. Python's / is integer division, calculated as looking at. This loop runs as long as there's something to search, meaning our left pointer hasn't passed the right one. Once they cross, we know we've exhausted the search space. We calculate the middle index of the current range. Python's / is integer division, so this gives us a whole number. If you're using another language that handles division differently, check out documentation online. This is the ideal case. We found the target. So we return the index where it lives. If the middle value is less than our target, that means the target must be to the right of mid. So we discard the left half, including mid, and shift our left pointer to mid +1. And if the middle value is greater than the target, then the target has to be on the left side. So we move the right pointer to mid -1, cutting off the right half. If we exit the loop without finding the target, we return -1, meaning the element wasn't found in the array. And there we have it. This version of binary search is what you'll use anytime you're directly looking for a number in a sorted array. Here's where binary search gets really powerful. Remember how in the vanilla version, we needed a sorted array to cut our search space in half? Turns out, we don't actually need a sorted array. All we really need is a monotonic condition. A monotonic condition is one that only changes in one direction. If it's increasing, it won't ever decrease. And if it's decreasing, it won't ever increase. The reason this is powerful is because we can make definitive claims about what happens past a certain point. For example, take a look at the graph on screen. At the point where x equals 5, y equals 100. What if I asked you, will all the y values to the left of this be smaller than 100? On the monotonic slope, we can definitively say yes. So we know that every value left of this is smaller and every value right of this is larger. But on the non-monotonic slope, we can't say that for certain because some values to the left are higher while some are lower. Doesn't this sound familiar? This is the exact premise that our vanilla binary search is based on. We look at a middle value, and because we know everything to the left is smaller and everything to the right is larger, we can cut out half of the list immediately. So having a sorted array is a type of monotonic condition, but there are other types that don't appear as sorted arrays. Let's say we have a function fx that returns either true or false. If we plot the values of fx over a range, it might look like this. Once the function turns true, it stays true. That's what makes it monotonic. It only transitions once and in one direction. Binary search can help us find that first true, the boundary, in logarithmic time, as long as we can write a feasible function that answers, is this index valid? This comes up a lot in problems such as ones where you're not given a sorted array, but you're trying to minimize or maximize something, and you can check whether a solution is valid for a given guess. Sort of makes sense? Let's take a look at the template line by line, and I'm sure it will make more sense. We're still using 2 pointers to define our search space. Nothing new yet. We keep track of the best candidate we've seen so far. If we find a position that returns true, we store it here, but keep searching left to see if there's an even earlier one. Classic binary search loop. We keep going until we've narrowed down the search space. Grab the midpoint as usual. Here's where things get different. We're not comparing values directly. Instead, we check if this index satisfies some condition. Think of this as asking, is this index good enough? If it is good enough, we store it as a possible answer, and then move left in case there's an earlier index that also works. This is the key move when you're trying to find the first valid solution. If mid is not feasible, we discard it and move right. Finally, we return the best answer we found, or negative one if nothing was ever feasible. This template might feel abstract at first, but once you plug it into a real problem, it clicks. Now let's plug that pattern into a real problem to see it in action. We're given a sorted array of booleans. All the falses come first, followed by a bunch of trues, and our job is to find the first index where the value is true. This setup is a classic monotonic condition. Once the array turns true, it stays true. It never flips back. So the array might not look traditionally sorted, but it still has that one directional property we need. So how do we find that first true efficiently? Binary search. We start by setting our usual left and right pointers to cover the full array, and we'll keep track of the best candidate we've seen so far, the earliest index that's returned true. Inside the loop, we grab the midpoint and ask, is this index good enough? If the value at that index is true, that means it could be our answer. But we're greedy here. We want the first true, so we update our boundary and keep searching to the left. If it's false, then this index and everything before it is invalid. So we shift our search to the right. This is the core idea of binary search on a feasibility function. We're not comparing values in the usual way. We're asking yes/no questions about whether the index satisfies the condition. That lets us confidently shrink the search space in the right direction. Once the loop ends, we return the best index we found. If the array was all false, that fallback value of -1 gets returned. This approach lets us find the boundary, the first true, in logarithmic time, no matter how big the array is. Pretty slick, right? Let's tap. Tackle a classic interview problem. Find the minimum in a rotated sorted array. We're given a sorted array that's been rotated at some unknown pivot. So something like 10, 20, 30, 40, 50 might become 30, 40, 50, 10, 20. Our goal is to find the index of the smallest number in that array. At first, it might seem like binary search won't help here. The array isn't fully sorted anymore. But if you look closely, there's still structure we can use. Before the rotation point, the numbers are increasing. Then suddenly, they drop. That drop is the pivot. And the smallest number sits right at that turning point. What's cool is that this creates a kind of split in the array. Every number before the minimum is greater than the last number in the array, and every number starting from the minimum is less than or equal to the last number. That's a one-way transition. We've got a yes or no condition that only flips once. In other words, a monotonic pattern. So for each index, we can ask a question like, is this number less than or equal to the last number in the array? This gives us a series of false values followed by trues. And now the problem becomes, find the first index where the answer is true. If you've already seen the pattern for finding the first true in a Boolean array, this should feel familiar. We're going to apply that same boundary-finding binary search here. Let's walk through the code logic. We start with 2 pointers, left and right, covering the whole array. We also track the best candidate index we've seen so far. Each loop, we find the midpoint and ask our condition. Is this number less than or equal to the last number? If the answer is yes, we store that index and move left, looking for an earlier one. If the answer is no, we know we're still in the too big part of the array. If the answer is yes, we store that in with the pointer's smallest number, even though the array gray looks unsorted, the key is that the condition we're testing is monotonic, which makes binary search possible. It's a clever way to turn a tricky-looking array into something we can solve in logarithmic time. BFS, breadth. We look closely at the pivot. This gives us should feel far, each whole array. We also too big part of the array, so we shift right. Eventually, the pointers converge. And at that point, we found the boundary, the index of the smallest number. To something we can is one of the most common and powerful patterns for traversing non-linear structures like trees and graphs. The core idea is this. You explore the structure level by level, start at the root or source node, then visit all its neighbors, then all their neighbors, and so on, before going deeper. This pattern is useful because it naturally gives you the shortest number of steps to reach something, a clean level order traversal, and a guaranteed way to explore everything evenly and fairly. At the heart of BFS is a simple tool, a queue. This queue ensures we always explore nodes in the exact order we discovered them, first in, first out. But how we apply this differs slightly depending on whether we're working with a tree or a graph. Let's break down both cases. Trees are a special kind of graph that don't have cycles, meaning you can't loop back to a node you've already visited. That makes BFS on trees simpler. You don't need a visited set, because the structure itself guarantees no repeats. Here's the exact template for running BFS on a tree. Let's break it down. We start with the root node and place it into a queue. While the queue isn't empty, we remove the first node, FIFO. We look at all of its children. If any child meets the goal, we return it. Otherwise, we add the children to the queue and keep going. The queue ensures that we always finish one level before moving to the next. This is what makes BFS so great for things like finding the shortest path in a tree or processing level by level. And because trees are acyclic by definition, we don't need to worry about visiting the same node twice, which simplifies the logic a lot. Use this pattern when you're traversing a tree from top to bottom or root to leaves, or when you care about depth, distance, or level-based logic, or if you're looking for the first match or the closest node to the root. As long as you're working with a true tree, this version is clean and efficient, but once cycles are possible, we need something more. Graphs are more general than trees. They can have cycles, loops, and multiple connections between nodes, which means you can revisit the same node more than once if you're not careful. To prevent this, BFS on a graph must track visited nodes. Otherwise, you'll either do redundant work, or worse, get stuck in an infinite loop. Here's the template for graph BFS. Let's break it down. Start with the root node in the queue and in the visited set. While the queue isn't empty, pop the next node from the front. Look at all of its neighbors. If a neighbor has already been visited, skip it. Otherwise, mark it as visited and enqueue it. This version guarantees two things. Every node is visited once you never enter a cycle or revisit paths unnecessarily. The key move here is when we mark nodes as visited. We do it when we enqueue them, not when we process them. That way we avoid adding the same node more than once. Use this version when you're working with grids, adjacency lists, or networks. The structure can contain cycles or duplicate paths. You need to find the shortest number of steps or minimum moves. You're exploring possible states in puzzles, games, or logic problems. BFS on graphs is especially useful when all edges or moves have the same cost, because it will always find the shortest path first. Both versions, for trees and graphs, follow the same fundamental structure. A queue for the current layer of exploration. A loop to isn't empty.